you very much, both for the invitation and for this these few days. It was great being here in Antwerp. So today I'm going to speak, as the title suggests, about various exact structures in additive categories and what happens when you change them. And you should expect some sort of connection between them. The plan of the talk is that first I'm going to give you some motivation about the phenomenon in the category of chain complexes and what happens there when you consider different exact structures. Then we're going to do a small pause and define some notions in greater detail. And then we're going to work in some more abstract categories and try to see if they behave like complexes or not. Okay, so I'm going to start with the motivation. Okay, so consider R to be a ring, and I'm going to denote with model R right are modules. I'm not going to mention right ever again. So if it is on the right, it's right. If it is on the left, it's left from now on. And with this, I'm going to denote complexes of our modules. Okay. So this is an additive category. This is an additive category. This is also an additive category. Okay. And in this additive category, we can consider two different exact structures. So let's start by the abelian one, which most of you should be comfortable with. So this category is not just an additive category, it's an abelian category. Being abelian, it's mostly an inherent property. So either you are or you are not. So in an abelian category, I'm going to give you some facts that work for complexes, and then we're going to see how these can be generalized in an exact category. One fact is that this category has projective objects. And the projective objects in this case are given by disks in degree Q of some object P. And when I say disk, I mean complexes. So what do? You have complexes where in degree Q and degree Q plus 1, you have this R module P, identity between them, is 0 everywhere else. And this P was to be a projective R module. Okay? The only one can define the injectives, where you take again disks in degree Q of an injective R module, but for the injective case, you put the injective R module in degree Q and then to degree Q minus 1. Okay? So these are your categorical projectives, and in fact, the categorical projectives in the category of chain complexes are the additive closures of this Q, where Q runs the integers, and P runs all the projective R modules. Okay?
Sorry. Like, is it automatic? Like, do you also have to add summations, or is it, does it come from?
Yeah, this is what I mean.
Okay. Yeah.
So every projective is going to be a direct sum.
A direct sum.
Something like this. Okay. The other fact is that there is a model structure which I'm going to define better in a bit. And this model structure is given by what is called a Hardy triple, which we have as the easy projectives, cyclic complexes, and everything. So this means in particular that this weird class of dg projectives, which are, you can think them as homotopically projected complexes with projected terms. Okay? A cyclic is complex that is acyclic, so it's an exact sequence of R modules, and these are going to be your trivial objects, these are the cofactorant objects, everything is going to be fibrant in this exact model structure. And when you have an exact model structure, then you can define the homotopy category structure, and this homotopy category, let's say complexes, in this case is nothing more than the derived category of the ring. Okay? This means that the weak equivalencies that you assume in this model structure are going to be quasi-isomorphisms. Now, what happens if I take, instead of the abelian exact structure, the degreewise split? Okay? So let's say degreewise split. Does everyone know what an exact structure is, or should I mention something? Okay, so okay, but you know what an abelian category is and what short exact sequences is. Okay, so in an abelian category, you have short exact sequences, and with them you do homological algebra. In an exact category, you don't take the class of all short exact sequences, but you have some of them that are admissible. So you choose a class of short exact sequences that you like, and you do homological algebra only with them. Okay, so in this case, you want to say degreewise split exact structure. Let's say in quotes that the short exact sequence here are sequences of complexes of R modules such that in each degree this short exact sequence splits in modal. Okay, so now you can only do homological algebra considering short exact sequences of this form. Okay, if it doesn't split degree-wise, it doesn't affect us to what we're going to do. Now, this has some implications in the things that we mentioned before. So now that your short exact sequences are of this form, your projectives are going to change. So what are the projectives here? They're going to be induces as before, but now here you are allowed to put any module. Okay, and why is this? So the projectives have the nice property that when you have Holm from a projective to any other module, when you apply Holm of a projective to short exact sequence, it remains exact. Okay. Now that your short exact sequences are such that when you go to degree-wise, they all split. In particular, it means that this functor is going to be exact for anything that you put here, because every short exact sequence is going to split. So it will remain exact by definition. Okay? So here I'm allowed now to take any module, which means that the projectives are just going to be everything. And then you have again a model structure where now everything is going to be cofibrillant. The trivial objects are going to be projectives, which in this case we happen to coincide with the projectives, and everything is going to be fibrillant. Now, this is immediate from the fact that here I omitted writing about the injectives, but I told you that here if you plug in an injective, and you change a little bit the degrees, you will get the exact complexes. So here you put everything. So you expect that the projective and the exactives are going to be the same. Now the homotopy category here, with the degree-wise, let's say exact structure, is proven by Happel to be the homotopy category of complexes. Okay? So these are complexes, modulus, and chain homotopys. And this is the result from Happel from the 80s. Okay. Now it is a well-known fact that we take here, actually let's start with the fact that the degree-wise split exact structure is a substructure of the abelian. Okay? It is clear? So this inclusion of exact structures here is going to induce a map between the homotopy categories. Between the homotopy categories. Okay? Now we know from Verdier that this is indeed the Verdier localization functor, and in particular it has left and right adjoints. This is taking projective resolution, this is taking injective resolutions, and there is a kernel here, and the kernel is exactly the acyclic complexes inside the homotopy category. Okay? And also you get some adjoints here. And this is a recollement diagram, and this was proven that it is a recollement diagram by M. Krause in 2005. So the question is, if I replace complexes with some exact category E, not exact, let's say E. And in this additive category, I assume two exact structures that behave like this. Okay? And let's call S1 inside S2 exact structures on E. Then, if I call this star, the question is there star for let's say. So if I replace complexes with a nice enough exact category, do I get some sort of a localization sequence as I get for complexes? This is what we are going to try to answer today. So to do that, we will need some triangulated categories. Here, I compare the triangulated categories that appear as homotopy categories of some model structure. Okay, so we're going to need to be able to construct some triangulated categories in an exact category. So let's move to section 2 of the talk, which is going to be exact model structures from Gorenstein projective objects. Okay, a lot of unfamiliar words probably. I'm going to define them slowly, one by one. And I'm going to start from the last one, what is a Gorenstein projective object. So I'm going to call it totally cyclic complex projectives. And I'm never going to write this again. I'm going to write it like this. And a cyclic complex projective terms. This is everything in an additive category. Okay. It's an acyclic complex of projectives. That is, you have, let's say, P bullet. This complex is exact. Every P that appears here is a projective object in E. And now we have to determine what total means. It means that for any Q that is also a projective object in E, this guy here is an exact complex of abelian groups. Okay. So you know that if you Holm, if you put Q here and you Holm it, then you get an exact complex since you start from an exact complex. But now what you are asking is that it remains exact also if you put the projectives on the other side of the Holm. Okay. Now, yes.
Sorry, small technical question. When you say projective object of E, you mean projective
I mean
with
that,
respect to some kind of epimorphism?
Yeah, I mean just that in whatever exact structure you have, this functor is exact.
Ah, okay. Yeah, that makes sense.
Okay.
Okay. Sorry. So the Holm is the internal Holm, right? The usual Holm complex.
The Holm is just the Holm functor. I'm not taking internal
Okay.
What I was asking is, isn't it always the case that if P is projective in every degree, then the complex that does Holm P is an exact functor? Maybe not. Probably not. Okay.
I don't have a counterexample ready for you, but it's not the case.
Okay.
Okay, so now I apologize to for keeping notes, but I'm going to change here the derivative. So I'm going to particularly consider this. So here, this differential has a co-kernel, okay? And this co-kernel is the zero cycles, okay? And then you embed it here and you continue. Now, let's call this Z, okay? The object Z is called Gorenstein projective if it is isomorphic to the zero CZG of some total and secant complex projectives. Okay. Now, every other CZG, so Z1 here, Z2, and so on, are going to be again Gorenstein projective objects. Okay. And one remark that I would like to make here is that if there is a Gorenstein projective that appears as the CZG of the total acyclic complex of projective P and of another one, let's call it P prime, okay, then these two total acyclic complex of projectives are projective equivalent, which means that the terms of the complex are going to differ only from a projective sum. Okay, so for all intents and purposes, for us it's the same. Okay, so Z doesn't depend on the choice that we are going to make here. Okay, dually we can define Gorenstein injectives by defining total acyclic complexes of the injective modules and so on. Right. So now let's try to tackle the elephant in the room, which is the exact structures, exact model structures. So an exact model structure on an additive category E, on an exact category E, is a triple of classes of morphisms, which we're going to call cofibrations, with equivalencies, and fibrations, that are compatible with the exact structure, and they satisfy some axioms. Now, I'm not going to tell you what the axioms are and how the compatibility works, because we are going to spend the next hour speaking about this. And you have to believe me that this is useful. And why it is useful? Because the idea is that every time that you are working in a category, abelian, exact, it doesn't matter, and you have a class of morphisms that you really want to make as a morphism, but they're not, there is, in principle, a model structure in the background that has this morphism as weak equivalences. Okay? And then the idea is we formally invert them. The weak equivalences, and define the homotopy category of this model structure, which is going to be just the localization with respect to weak equivalences. Okay? So in this homotopy category, the weak equivalences are isomorphisms. Right. Any questions so far, maybe? In model categories, we have some special objects. And I'm going to define these classes as C, which are all the objects in E, such that the map from the 0 object to X is a cofibration, and I'm going to call these objects cofibrants. W, which I will define in a bit, and F, which are all the objects X in E, such that this map now is a fibration. These are called the fibrant objects, and W are the trivial objects, and are the objects in E, such that either this map or this map is a weak equivalence. Okay? So when we pass to the homotopy category, all these objects in W are going to be 0. Now, in principle, these 3 classes of objects do not determine the model structure. Okay? You have to work with the morphisms. But I'm doing algebra and not algebraic topology, so all of my categories are algebraic in a sense. So we are lucky enough that these can determine the model structure in the end. But for this, I have to introduce you to the notation of the proportion pair. So a pair of classes, let's call them A and B in E, is called a proportion pair. If you have that A is the x1 left orthogonal of B, and B is the x1 right orthogonal of A. And what do I mean by this? I mean that every time that we have x1 between an object A and B, A in curly A, B in curly B, this vanishes. For any A in A, for any B in B. Okay? So this is what a torsion pair is. Maybe you are familiar with torsion pairs, some of you, I do not know. This is just the x1 version of them. And in particular, we are going to call A and B a complete torsion pair. If any object E in your category fits these sort of exact sequences, or maybe I will leave this sequences for now. In sort of exact sequences of the form. Now you have your object E, and you approximate it from the right with an object in your class B. And the cocurrent has to be in the class A. And you can do the same actually from the left. So now you approximate with an A on the left. The kernel has to be B. Now, what does this mean? It means that a Cotorson pair generalizes the notion of projective and injective objects. Okay? And this will be clear if I take as an example A, be the class of projectives. Then you have to, let's say, advantages. Okay? And then you have to calculate what is B, so the x1 orthogonal to the right. So you have to find all the modules B such that X from the projective to B advances. But this is every module. So B is going to be R. And what does this sort of exact sequence say in this case? That any object E, so what does this sort of exact sequence say to us? Every object, every R module E in your category has a projective recovery, and the kernel is any other module, which is true. This one is a little bit more technical, and I will leave it for now. Okay, so this is the main idea. Complete Cotorson pairs generalize projective objects, and dually you can also do injective objects. Okay, and why should one care about this? So, for some of you that might have seen the definition of a model structure before in the past, you know that they satisfy some lifting properties. And now maybe this is not clear by the definition, but Cotorson pairs have some lifting property between them, especially if you think of how projectives behave. So there is a theorem from Gillespie. Gillespie proved it for exact categories, but his work came after the work of Harvey, which proved it for abelian categories, which says that E is an exact category, and you have a bisection between exact model structures on E and complete Cotorson pairs let's say with, I'm going to write W thick, and I'm going to explain what does this mean when I'm going to give you how the bisection goes. So what we said that when you have an exact model structure or any model structure, you can define these classes of objects. Okay. If you have a model structure, this is going to automatically be thick. This is going to go into a Cotorson pair, into two Cotorson pairs, C, F intersection with W, and C intersection with W, F, and then you can go back. Also, if I have like a Cotorson pair C, W, I will need W to be thick because it will appear here to be thick. Okay. For people that already see model categories before, this is exactly the same as saying that a cofibration has a trivial fibrant co-kernel or something like this. Right. Okay. So.
But do you have to quotient out something on the right to get the bijection? Because you say that you get two pairs, or is that one pair?
No, they usually one of the Cotorson pairs is going to be a trivial, let's say, Cotorson pair. So everything is 0 or something like this, or everything projected most of the times. Yeah. So you have this, and most importantly, if I denote with ECF, the subcategory of E of all the cofibrant and fibrant objects, which sometimes are called bifibrant, okay? And then this is going to be a Frobenius exact category. What do I mean by Frobenius exact category? It means that it has enough projectives, it has enough injectives, and these two classes coincide between them. In this case, the projective injective objects are going to be exactly, let's say, the intersection of all three classes. Okay, so all the bifibrant objects that are also triggered. Makes sense, right? The homotopy category that you're going to get is the stable category of this Frobenius exact category. Okay? So, why is this theorem beautiful, in my opinion? Is that working with morphisms, like the definition of a model structure, is quite hard and tedious, while working with contortion pairs is more homological. You just have to check some X-balancing conditions. So this theorem allows you to create model structures out of some homological data. Okay? And this is exactly what we're going to use. So our setup is E is an exact category. That is weakly, idempotent complete. And it also has enough projectives. Okay, you can bypass having enough projectives by working with the injectives, but since I want to give you a symmetric picture of this recollement situation, I will give also enough projectives. Okay, otherwise you will get half the value. So it is half. Okay, so now projectives. Okay, and now I'm going to define the homology functor. Let's call it curly H. That we define as xi in E, where the antecedent of some Gorenstein projective object, and this goes to be okay, so this depends both on Z and on N. Okay. Okay. Now we are ready for a small lemma. Okay. So if I denote by caret Z class of Gorenstein projectives, and if I take S of Z, the set of all the series of these Gorenstein projective objects, then the contortion pair that I'm denoting by C of Z, Z, which is simply the contortion pair that is generated by the set, and what then is generated you take here your set, you take x1 orthogonal of it, and then you take the x1 orthogonal from the left of the x1 orthogonal of this. So it's like this. Okay? This in particular means that these objects here are going to be objects that are filtered by this set. Okay? Filtered by series of Bernoulli samples I used. Yeah, this is complete. If Z, let's say, is a set important, and let's say E is efficient. What do I mean by efficient is a special class of exact categories where the small object argument is satisfied, and then you can do a lot of set theory and somehow manage to prove that if this contortion pair is generated by set, then it's going to be complete. Okay, it's purely set theoretic, this argument. But I'm going to give you an idea of some examples of efficient categories. Your favorite Grothendieck category is going to be efficient. Complexes of your favorite Grothendieck category is going to be efficient. And in fact, it was already known that in Grothendieck categories, if you have contortion pairs generated by set, then they're complete. Okay.
What is it called? Grothendieck category?
Grothendieck satisfied. Okay. In which level of abelian categories are you comfortable with? 84? 85? Okay, it's an abelian category with this.
It's nice.
It's very, very nice. You have limits, exactly. You have very nice properties. Modar, that's cool with modar. It's Grothendieck. Okay, sieves over coherent sieves over nice schemes. They're Grothendieck. Sorry. Yeah.
I'm sorry, I was surprised by seeing only C and W instead of seeing the trivial fibrance.
Yeah, because here everything is going to be fibrant.
Ah, okay.
Okay, I forgot to mention this. Everything is going to be fibrant.
And is the idea here that like these currents are like the generating cofibrant, or is there no?
Yeah, right. So for you that among us that know what a cofibrant generation is, this is exactly that this class is cofibrantly generated. Okay. So let's go with theorem A. Okay. In the setup that we have, the following. So you have a contortion pair that is generated by these guys, okay, in an exact added and complete category with enough projectives. That now we're going to assume that for simplicity that it's efficient and Z is a set, okay. You can actually manually prove that this contortion pair is going to be complete in some cases, even if these conditions do not hold. But for now, I'm going to assume that we're in the setup of lemma 1. So an object X is going to be trivial if and only if the first homology of X, as I defined it here, vanishes for any Z, for any N. And a map phi is going to be a weak equivalence if and only if H1 of phi is an isomorphism. But unfortunately here it's not so nice. You have to check also HC. Okay. And again, you get here that the homotopy category of E is going to be the say E stable by 5 different objects, but since everything is final, this is just going to be the stable category of 5 different objects. Okay, so now we have our yeah, and this is going to be triangulated. Triangulated categories. We are comfortable with
I will not ask. I've heard before.
Okay, can you tell before? I will. Okay, so you have a very nice exact category. You have some class of homological objects, which in this case are going to be Gorenstein projective objects. You can do everything you said before with Gorenstein injectives. It works when just passing to the opposite category. And you get out of them some nice triangulated categories that in particular are going to be algebraic. So what happens if, like in complexes, I assume that they have two exact structures that give me something like this. Something like this. Okay? So let's say B. Again, as in setup. Now assume also that S1 inside S2 are some exact structures on E such that theorem A gives you homotopy E1 and homotopy E2. Okay? So you assume two exact structures instead of only one, you get two homotopy categories. Okay? And assume also that I think I messed my indexes. Yeah. Assume also that the weak equivalencies in one are contained in the weak equivalencies, the trivial objects of the second one are contained in the trivial object of the first one. Okay? Then you have that if I call this inclusion here I induces a Verdier localization, which I'm going to call it I lower star, from the homotopy category of E2 to the homotopy category of E1. And what I mean with Verdier localization is that the homotopy category of E1 is going to be equivalent to the homotopy category of E2 modulo the trivial objects of the model structure that gives the homotopy E1, but you view them as a full subcategory of the homotopy category of E2. Okay? It's the same idea as in that recollement diagram that we had, that we took acyclic complexes in the homotopy category, not in the direct category. Okay? And moreover, you have here your Verdier localization. You have the kernel of this localization that is going to be this W1. And now, if you take, what was it? Okay, if you take here the contortion pair generated by this set, these are called projective contortion pairs, because the intersection of these two classes is going to be the projective object always. You are going to get a left adjoint here and a left adjoint here. If you assume here lemma 1 opposite theorem A opposite and you work with the injectives, then you're going to get also this right adjoints. So this is called endowing colocalization, this is called endowing localization. If you have both of them, this is a recollement of triangulated categories. Okay, how much time do I have?
13 more minutes?
How much?
13?
13. Okay, then you are unlucky. Because I'm going to speak to give you an application of this. But before I give you the application, I would like to comment a little bit on that theorem. Something that I found a bit peculiar is that these adjoint functors here means that this homotopy category fully embeds inside this homotopy category. Okay? And what I find strange is that we assume something that has less information here, and you get something that has more information here. I just leave this here. If someone knows why this might happen, it's okay. But yeah, I find it quite strange, also for the derived category and the homotopy category. Okay, so let's do an application now. We're going to do it in the setup of what I call relative Q-shaped analogous algebra. Right, so most of you are comfortable doing homological algebra with chain complexes, called chain complexes, doesn't matter. What is a chain complex? Let's say that it's a diagram Q indexed by the integers and so on. And you have some arrows here such that the composition of any two consecutive arrows goes to 0. Now, this diagram is called a quiver because it's an oriented diagram. And if I take representations of this quiver, then this is the same as taking functors from the quiver Q, viewed as a small category where the objects are the vertices and the arrows is the home sets generated by the arrows. Okay, this is, and let's take the values in some mod A for some algebra A. Okay, A here is a K axis. Now, what does this mean? It means that in every vertex I put my favorite A module. In every arrow I put a linear map between two A modules, okay? And I still ask the composition to go to 0. This complexes. Okay. So this complexes of A modules. Now, the idea of Holm and Jorgensen was to replace, let's call this QCPX, with some other nice, that I'm not going to explain, Qs, and do homological algebra on those quivers instead of doing it with complexes. Okay? And this worked in a sense that they managed to introduce the notion of what we call the Q-shaped category of A, which is defined as the homotopy category of some very nice model category in this functor category. Okay? And yeah, they defined some model structure here. They took the homotopy category. They defined as, they call it Q-shaped category. And for the special case that Q is QCPX, this is just the derived category. So we're speaking about the generalization of the idea of the derived category. Now, you remember from the very first thing that we wrote in the blackboard about defining exact structures in complexes. The abelian one was clear. The exact one, we have to go degreewise. Okay? So we're going to follow the same principle in this category. I will leave it as a rep for now. Okay? So how are we going to define exact structures in the category rep Q? Now, Q here, when I say Q, I don't mean this specific QCPX, I mean any Q that is nice enough. Okay? So take your favorite exact structure in modules. I'm going to define this E. For example, this can be the abelian exact structure, this can be the split exact structure, this can be the pure exact structure. Take anything and define in rep Q. Let's call it rep Q comma A because we take values in A. Conflations or sort exact sequences as follows. So you have a sort exact sequence in rep Q comma A. If and only if. Now these are functors, okay? So in each object Q of my big Q, I get something that is name, okay? So for each object Q, I want this to be an exact sequence in mod A with the exact structure, okay? So if I want the abelian exact structure, it doesn't matter, I take anything here, okay? If I want the degree-wise split, which here I'm going to call it object-wise split because you don't have degree, you have objects. I'm going to ask here every sequence to split. Okay? Object-wise pure exact structure if these sequences are pure, and so on. And what we were able to prove here is that so here we have the following. There is a triple adjunction from rep Q comma A to mod A, where here you just have evaluation at the vertex Q. Okay, you're just taking a functor from Q to A mod and you evaluate it to the vertex Q or the object Q. And then you can go back with a left or a right adjoint. I'm going to give you this guy here, FQ, and we're going to define it as FQ of a name module M. It's just taking the representable functor of the vertex Q, and then you tensor it with the module M. These guys are going to be projectives with respect to any exact structure that I'm going to give to rep Q comma A. Okay, and maybe I should mention that all these functors here are exact, also with any exact structure that I put to rep Q comma A. And yeah, so these are the candidates for our projective objects. They are projectives if M is projective into a model with the exact structure that you define. Okay, sorry. Right, and we need to define also some other functors that I'm going to call stock functors that give you the module M in the vertex Q and 0 everywhere else. Okay, these are called stocks. And this guy is a Gorenstein projective if and only if M is a Gorenstein projective for A mode. Okay? So we are again in the setup of the theorem. Okay? So now I take as the class Z, I take stocks. Okay? I generate a contortion pair out of it, and I take a homotopy category. Right? So let's see what we can get out of this in this weird homological algebra setting. So take the category mode A with, let's call it abelian structure, and I will take, let's call this actually theta 1, and let's take theta 2 mode A with split exact structure. Okay? Split means that every sort exact sequence of A modules is going to be a split exact sequence. These two structures are contained like this. So theta 2 is inside theta 1, obviously. And they induce some exact structures in RFQ on A. Theta 2, theta 1. Okay, now theorem B tells us that if I pass the homotopy category of this 2, A, theta 2, then I have the functor to the homotopy category, blah blah blah. Doesn't matter, do not write it, I'm going to erase it in a bit. That will give you this recollement situation. Okay? But what you can solve is that for theta 1 being the abelian exact structure, the contortion pair that you get from theorem A, or actually the lemma that I just erased, is going to be the same contortion pair that Holm and Jorgensen had to define the Q-set derived category. Okay? Our contortion pair, for the second exact structure, we are going to get another contortion pair, which is going to be, since you ask sort exact sequences, such that every time that we evaluate in a vertex, we get a split sequence of A modules. But you're going to get as a contortion pair here, it's going to be everything is cofibrant, the trivial objects are the projectives, and everything is fibrant as well, just like in the homotopy category. So we thought of calling this the homotopy category, like you said, homotopy category. And then applying the theorem before, you're going to have here projective and injective resolutions that embed the Q-set derived category inside the Q-set homotopy category. And here we are going to have the kernel, which is going to be the trivial object of this exact model structure used inside the homotopy category. It's we are going to call Q-shaped acyclic complexes. And then complete the picture. And what does this give you? For example, from Q being the figure that gives you the complexes, you get the result of Krause from before. And if some of you are still not convinced that this is exactly the notion of the Q-shaped derived homotopy category that should be, we also have a corollary that says that if A has finite global dimension, then the Q-shaped derived category of A is nothing more than the Q-shaped homotopy category of the projectives of A. And what I mean by this is, let's see now, I take here my functors take value projective. Not okay, and this is again a classic result that happens in the derived category of the ring. And I think that I will stop here.